Okay, so we were saying that if we want to study the force balance on this element, sum of forces equals to MA, we need to consider the dominant forces acting on it. So let's say for the body force, we take the weight. The weight is for this element is m, the mass, which is dm, because it's a small mass, times g. And we can replace dm by, of course, here, look, here, I don't know if y is the vertical direction. So if I want to have the most general case scenario, I can just consider that the weight has a certain random orientation in this frame, and I decompose it into x, y, z component. And I say that weight vector is dm times the g vector. And dm is rho dv, so it's rho times dx times dy times dz. And g vector can be decomposed into x component, so you have gx, gy, and gz. Okay, if y is the vertical direction, then gy is minus g, and gx, gz will be 0. Okay, but since we are developing a general case, we can consider a random orientation for x, y, and z. Now, other type of forces, as we said, you have the pressure forces. So let's say I need to determine the pressure field. So if I know, let's say the pressure at this face is Px, then at the face, at the second face here, it's pressure at x plus dx. And I can use Taylor expansion to relate these pressures. So I can write that pressure at x plus dx is equal to the pressure at x plus del p by del x dx. And as you can see already, the problem is very complex because I have the velocity that is unknown, the pressure field that is unknown, and I want to couple these. I want to relate pressure and velocity. This is why we'll see in this course we have coupling algorithm between velocity and pressure. We'll see how we can use them to correlate pressure and velocity. So at this phase, the pressure is Px plus del P by del X dx. And just pay attention, pressure forces are always acting towards your control volume. So pressure forces from this side will be to the right. Pressure forces from this side will be to the left. And to determine the value of pressure force, you multiply the pressure by the area on which it's acting. So for Px, it's acting on this area, which is equal to dy times dz. So you get that it's Px times dy times dz. While for the other face here, it's pressure at x plus dx times dy dz. But as we said, in the opposite sense, so it will act in the negative direction. Okay. Now, other type you will do for pressure forces, you will consider pressure on all surfaces. And as we did for pressure here, you will do it for these two faces and for these two. So you will obtain all pressure forces acting on your element. Now, also you can add stress if you want shear forces. Shear forces are forces parallel to the your faces. Okay, so you can have shear forces, for example, along x direction here. Okay, in these faces also you have shear forces along z direction. So you imagine how many forces do you have. What you should do then, you should add all of these forces and say that sum of forces is equal to ma. Okay, we'll see this again in detail after. Now I will just expose for you the results after simplifications what will give you the Newton law? It will give you the three momentum equations in X, Y, and Z. So after you do your simplifications, you will get the following. And I will explain the terms. What are the different terms? So from this side, you will have terms of acceleration, because you will simplify M. Yani, when you put sum of forces equal MA, you will see that the mass term will be simplified from both sides. So you'll end up with A equal to sum of forces per unit mass. Okay? And so this term will represent the total acceleration along X. We'll see together, and you have seen from fluid mechanics, that any property in, if you want, in a fluid can have variation with time and with space. So here, when we work in Cartesian frame X, Y, Z, any component, which is velocity, pressure, acceleration, any variable, can be expressed function of time and position. Okay, this is why you know that in general the acceleration vector is the derivative of velocity vector with respect to time. And when you derive any quantity in a field, you should consider that this quantity is affected by four variables, which are X, Y, Z, and time. Okay, so you will use the concept of partial derivative, and you can establish that the derivative of a certain vector with respect to time, this is called total derivative, okay, with respect to time, is equal to the local derivative, and we'll explain the physical meaning of local derivative, plus derivative related to change in space. So this will represent variation with respect to space. Okay, so what is the meaning of local acceleration and convective acceleration? If you are in a flow field and you are observing a certain point, okay, let's say this point is surrounded by other points. So let's say we are considering 1D application. You can have, if you observe this point here, when you observe a specific location, this means you are not considering variation in space. You are just considering the position of interest. So it can only vary with time. So this is called local acceleration. If you are observing variation of velocity, del U by del T will give you the local acceleration, which means how the velocity of this point is varying with time. Now, why we have another type of acceleration, which is convective acceleration? Because if you have a particle moving in the domain, this particle will move from one location to the other. Okay, and if the velocity is changing with space, is changing with location, then my particle will undergo acceleration or deceleration as it go from one position to the other. So to take this into account, it will be considered through the convective acceleration, which represent the acceleration due to variation in space. And since you are conducting analysis in the most general 3D case, so you can have variation of velocity with X, variation with Y, and variation with Z. Okay, so in total, your total acceleration will be the summation of local and convective acceleration. Of course, if you are dealing with steady applications, so when you select an ANSYS Fluent study, it will automatically know that I don't have a transient term. So automatically ANSYS, when doing the numerical calculation, it will drop all derivatives, all local derivatives with respect to time. Okay, and it will then consider only a variation with respect to space. Now, if I want to do the analysis of the other side will represent forces per unit mass, because I divided sum of forces equal MA. I divided both sides when I did simplification by M. So when I divided by M, I will obtain from one side the acceleration term, and from the other side, I will obtain force per unit mass. Now, if I do analysis of my terms, this is the gravitational field value. You know that vector G, okay, is related to the gravitational field. It will give you the weight, so it's related to the weight. So we know that the weight is m times g. So when we divide by m, the weight per unit mass will give us vector g. This is why this represents the body forces or gravity force per unit mass, and it can have three components: one in x, one in y, and one in z. And in particular, if our y-axis is the vertical direction, these two will drop out. Okay. Now, the second term is pressure gradient force per unit mass. As I told you, you have pressure forces. If you put all pressure forces and you do the balance, you will see that because of Taylor expansion, when you do the difference between the pressure forces, the terms that will remain will be related, and after simplification will be minus 1 over rho del p by del x along x, minus 1 over rho del p by del y along y, and minus 1 over rho del p by del z along z. So these are the pressure gradient forces per unit mass. The last term is for viscous forces. Now, from where we got this term, this is from shear forces, okay? So we said that we have shear forces, and shear is related to viscosity. And we will go into more details and when we review conservation equations. So because shear for a Newtonian fluid, you have certain relation between a shear and viscosity, and after you simplify, you take into consideration these relations. For a Newtonian fluids, the viscosity is constant. So if you deal with mu constant and you take constant density also, you obtain this result. If mu and rho are not constant, it is much more complex. In this case, we don't obtain Navier-Stokes equation. Navier-Stokes equations consider that rho and mu are constant. If they are not constant, you will have much more complicated equations, and then you will deal with these equations to solve, okay? And you will not obtain this form, you will obtain another form, but at the end it will relate viscosity, but then viscosity will be variable, will not be a constant. This will add your unknowns, because already you have as unknowns here the velocity field. So you don't know u, you don't know v, you don't know w. You need to find how they vary with time and position. And you have the pressure field p, which can vary with x, y, and z. And in addition, if the fluid is not a Newtonian, you should also have formulas to find how mu is varying. And you need equation for variation of mu, which will complicate results. And if your flow is incompressible, also this will complicate your relations, because rho also then will be function of time, of x and y and z, which will really complicate things. So Navier-Stokes is a particular case for fluids that have constant viscosity, constant density. In case these are not constant, you will obtain more complex equations, and you should solve for the variation of viscosity and density in addition to velocity and pressure with space and time. So already Navier-Stokes are really complex equations, and they don't always have analytical solution. They only present analytical solutions in some simplified cases that we talked about, like laminar flow in duct, in pipe systems, flow between parallel plates, etc. Okay. Now, what if the case is more complex? What should we do? So now this will introduce us to the idea of LCFT. Okay, so this Navier-Stokes equation constitute non-linear partial differential equation, and we tried a lot in research to come up with mathematical solution for these equations, but we found out that there is no general closed form solution for these Navier-Stokes relations, and we offered very high prices, economical prices for the scientists who can solve them, but it was not solved until now. We only obtained some closed form solution for specific problems, which are simple, as we said, like flow in circular dogs or flow in concentric annulus, etc. For more complex scenarios, we have seen that there is no analytical solution. So we should think about something else. And then we said we have two paths to follow if we cannot use analytical solution, or we should perform experiments. And you know that it's not easy to perform experiments in all cases. Sometimes it will cost a lot and it will need a lot of time. So it's true that experiments present the advantage that they can present the real case scenarios. They will take into consideration all physical situations. So no need to have any simplification, but they cost a lot and they take a lot of time. So if each time you need to vary a parameter, you need to conduct a new experiment, this will already take a lot of time from you. So another strategy will be to search for numerical solution. And numerical solution of these equations is called computational fluid dynamics, which is CFD. Okay, so in this course we will learn different techniques, different numerical techniques that will allow us to solve these complex differential relations. So in order to solve these equations, first we need to supply the geometry. We should know the geometry of our problem to be able to divide it into small parts. We should know the appropriate boundary conditions for the domain. So what are the inputs? We cannot solve if we don't know the inputs. Let's say in a room, if you want to solve for the velocity field and temperature field, you cannot solve if you don't know what is your HVAC system input temperature. So if the inlet temperature is 14 degrees, the solution will be different than if the inlet temperature is 20 degrees. So it's very important to determine the boundary conditions of the problem, and these will be inputs to your CFD software. So you should input them to your software, and he will perform the numerical calculations to give you the corresponding outputs. Now, if we have unsteady flows, we should add also initial conditions. So at t equals 0, we should specify what were the conditions, because this will affect the transient behavior of your solution. Now, in case it's possible to do some simplification, we do that. And for example, sometimes, let's say, some effects can be neglected. So when you include when you have sum of forces equal ma, you can have many type of forces: electrostatic, magnetic, body forces, buoyancy forces, etc. So sometimes from the application, you know what are the dominant forces in such application. So let's say for HVAC application, you don't have electrostatic forces, you don't have magnetic forces. So the dominant forces will be the weight, the body forces, let's say buoyancy forces. Buoyancy forces will be dominant if you have large variation in density of your fluid within space. If not, if your fluid, let's say, can be treated as incompressible, then there is no buoyancy effect. You can have other forces that will act on your system. So pressure forces will be more important. Let's say viscous forces will be more important. So you can simplify if you want negligible forces in case of we are dealing with momentum equation. Or for example, if you have a heat transfer application, you have several heat transfer. Sorry, do you have a question? Okay, so if you have a heat transfer application, for example, you have different processes that will affect your system. You have convection, you have conduction, you have radiation. In some problems, for example, radiation can be neglected, and some other problems it cannot. So we in literature we say that if we have gradient in temperature within the space smaller than 10 degrees, so if I don't have large variation in temperature within between surfaces of my space, I can neglect radiation. So this will simplify a lot the balance, the energy balance. So you can try to do simplifications that will not affect your a lot your results. So you can reach with a smaller time an accurate solution. So if possible, you perform all simplifications that can be done, and then you can, if you want to do analytical solution, you can try to integrate the equation and see if you have a closed form solution. If not, if you cannot reach a simple solution, you can go back to numerical techniques. And if you want to go to numerical techniques, you need to transform the differential equations to numerical equations. And we'll see together how this can be done and what are the different strategies to transform an equation from differential form to numerical form. So here in this slide, we can see an engineering problem that cannot be solved analytically. So if I have a car, I want to design a car, okay, and I want to test, let's say, I want to change its design in a way to reduce drag, for example. So I should study drag forces on the car, and I should study the effect of different curvature on the drag forces. This is a very complex problem, and it will require numerical simulation or experimental work because I cannot find analytical solution for this. So how to do this? I can run a simulation. I draw the geometry of my car and I put it in a wind tunnel, let's say, and I have a flow coming over it. And I study, if I'm using CFD, I can plot contours for the velocity profile. So how, if you want to have separation of your flow when it will hit the car, you will have flow separation, you will have formation of boundary layers around the car. And due to this, this will develop a certain drag total force, total resisting force on the car, which we call the drag force. So using the software, you can compute the drag force at each location and do the integral, do the summation to find the total drag force acting on your car. And this will allow you to compute the drag coefficient. So you can test several designs, several geometries to reduce this drag coefficient, to reduce drag forces on your car. So this can be a problem. You can also study what is the pressure variation on your car. So of course, the front part will be subjected to high pressure because you will have stagnation points, and then this will develop very high pressures at these points. So you should use materials that can sustain this pressure. So here you will enter the domain of mechanics of materials to determine which material should be used to avoid any deformation. Okay, etc. So this is a typical problem requiring computational fluid dynamics simulation. So now, as we said, we have always several ways to approach a problem, okay? And sometimes not all are possible. If the problem is complex, I might have reduction of possibilities for solution. So in general, the three ways of solution are the analytical or theoretical approach, the experimental approach, and the numerical one. Each one has its own advantages and disadvantages. When possible, the analytical solution is the best because it can give you accurate solution. Okay, it will give you exactly what the solution is. But the disadvantage is that it's restricted to very simplified problems, and in a lot of engineering applications, I cannot reach an analytical solution using my differential equations because they represent a much complex if you want form, and if I have complex geometry also, this will make the analytical solution not feasible. So this is why this approach is limited, because in many engineering applications it cannot work. Okay. The other two approaches are experimental and numerical. So now, as we said before, experiments have a high advantage that they will take into consideration all physical, if you want, the real physical situation will be considered as a whole. So I don't have to neglect anything, because I'm really testing in real case what is happening. This will give me a good idea about how my flow is varying, how my temperature is varying, etc. But the disadvantage is that I need a lot of time to perform it, and it will involve a very high cost. This is why I can use it, if you want, as a validation approach. So experimental approach is widely used with CFD as validation. What do we mean by this? When you will develop a CFD model, okay, sometimes you need to do some tuning. You need to alter some coefficients, you need to update some models in a way to give you results very close to the real case. So when we develop a model, we should test several meshes until reaching a convergent solution. And even the convergent solution can be, if you want, enhanced. So I can use finer size of mesh to give better results. So to help me to know if my CFD model is working or not, I can compare the results I get from CFD with the experiment. This is called validation procedure. So if I am able to reach error that is relatively very small, so I can calculate the relative error. If it's of order less than 10%, I can say that I validated my model with experiments. And then once it's validated, then no need to do everything experimentally, because my CFD model is working well. I can perform my parametric study, so to study the effects of inputs, of variation of different input parameters on my solution. I can perform this parametric analysis in CFD. So the numerical approach will use numerical techniques to solve for a problem. The disadvantage is that I obtain approximate results, not exact ones, but if I validate my model, I can reach results that are very close to the real case. So I can then rely on this numerical approach to study my system and conduct parametric study on it. When we say parametric study, this means that we identify the main parameters of the problem. So for example, for HVAC application, the main parameters will be the supply temperature, the supply velocity, the heat fluxes within the space, the heat sources in the space. So I can vary these and see how they affect the flow pattern and the temperature profile. And then I can conduct several simulations in CFD. And this is what we call parametric study, which will assess the effect of each parameter on my output. Okay. Any question on this? Okay, guys. So we are done for today. We'll continue next time. Bye bye.
Okay, doctor. Thank you. يعطيك العافية.
Merci,
Merci.
doctor.